General solutions. Normally when we see an equation like this, they'll say solve between 0 and 360, for instance. But obviously, we know from our graph, there actually would be an infinite number of solutions if we didn't specify between. So to generalize the solution, to come up with a formula, if you like, that would create every possible solution. So we'll look at sine theta first. Now, it all depends whether x is positive or x is negative, because that will dictate which quadrants we're talking about. So let's first of all look at the situation where x is positive. Okay, well, if it's positive, I know it could be in the first quadrant. The acute angle would be whatever the inverse sine of x is. Of course, it could be in the second quadrant, and again, the acute angle would be whatever inverse sine x is. So my solution would be inverse sine x or pi minus inverse sine x. Okay. If x was negative, however, what happens? Well, now we're going to be in the third quadrant. But remember, x is now negative. So the acute angle won't be the inverse sine of x. It'll be the inverse sine of negative x. Because to get an acute angle, I need that ratio to be positive. Okay. And then in the fourth quadrant, similar thing happens. The acute angle would be the inverse sine of negative x. So my two solutions are pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. But we've got a rule that allows us to deal with inverse sine of negative x, well, the inverse sine being an odd function. So I could rewrite that as pi minus the inverse sine of x, which you'll notice was one of the solutions when it was positive as well. And 2 pi plus the inverse sine of x, which actually is the same as the first solution in the other case. It's just that we've gone around the circle once. So it actually looks like it doesn't matter whether x is positive or whether x is negative. We come up with the same solutions. And of course we could add 2 pi to each of them and so on. So to generalize it, I can say, well, if sine theta is equal to x, x is going to equal, well, we know it's basically going to be the inverse sine of x, but it's going to be pi k, but it's going to alternate from plus minus, plus minus. So it starts off, I've got positive inverse sine x. The next solution is pi minus inverse sine x. The next solution is 2 pi plus inverse sine of x. And so the inverse sine will alternate. So to take into account that, in front of the inverse sine x, I put negative 1 to the power of k. And so that way when k is odd, it'll be minus, and when k is even, it'll be positive. And so there's my general solution for inverse sine. All right, let's do the same thing with cosine. If x is positive, now this time I'll be in the first quadrant or the fourth quadrant. Again, the acute angle will be inverse cos x. So I've got inverse cos x or 2 pi minus inverse cos x. Now if x is negative, so I'm in the second quadrant, but again, now because x is negative, the acute angle will be the inverse cos of negative x, or the third quadrant. So my solutions, pi minus the inverse cos of negative x, or pi plus. Now our relationship for inverse cos negative x, if you remember, was inverse cos negative x was pi minus the inverse cos of x. So this will become pi minus inverse cos of x, which just ends up being inverse cos of x, same as our first solution. The second one becomes pi plus pi minus inverse cos of x, 2 pi minus inverse cos of x, again, same as the second solution. So once again, does not matter whether x is positive or negative, we come up with the same solutions. And of course I could add 2 pi to each of these. So we've got inverse cos of x, 2 pi minus the inverse cos of x. The next solution then would be 2 pi plus the inverse cos of x. Then it would be 4 pi minus inverse, and so on. So the general solution for this one, if inverse cos of theta is x, we'll get multiples of 2 pi plus or minus inverse cos of x. All right, let's look at tan then to complete it. So first quadrant, oh sorry, not first quadrant, x is positive, which is in the first quadrant, but also the third quadrant. So this one we get inverse tan of x or pi plus. If tan is negative, we'll be in the second quadrant, but once again, x is now negative, so the acute angle would be inverse tan of negative x, or the fourth quadrant, which comes up with pi minus inverse tan of minus x, or 2 pi minus. All right, inverse tan, that was an odd function. So inverse tan of negative x is equal to the negative of inverse tan of x. So if we change these, I end up with pi plus the inverse tan of x, same as my second solution. 2 pi plus, which effectively is the same as my first solution. So yet again, it doesn't actually matter whether x is positive or x is negative. We'll come up with the same general solutions. So if tan theta is equal to x, for this one, it's simply going to be multiples of pi plus. So not plus or minus like the inverse cos one, just plus. It's always pi plus, 2 pi plus, 3 pi plus, and so on and so on. Okay, so let's apply it. There's one of our exact values, which hopefully we remember is. So we've got pi k, and then I've got the minus 1 to the power of k to take into effect that with inverse sine, it was plus, and so on. Inverse sine root 3 on 2, which we now have established is pi on 3. Good. So there's my final solution, where k is, of course, a whole number or an integer. Now, just to show you that it does generate the solutions, if we were looking for answers between 0 and 2 pi, if I substitute different numbers in, well, if I substitute in 0, pi k obviously is 0, minus 1 to the power of 0 is 1, I get pi on 3. And if k is equal to 1, I get pi minus pi on 3. There are the two solutions that we would expect if it's between 0 and 2 pi. Let's try a cosine one. Negative 1 on root 2. Okay. See how we go. It's going to be 2 pi k plus or minus for inverse cos. Inverse cos of minus 1 on root 2 minus pi and 4. What is it? No, it's not pi and 4. It's 3 pi and 4. Think of inverse cos function. The range is 0 to 2 pi. Inverse cos never gives a negative answer. Right? So negative means I'm in the second quadrant then for inverse cos. So it should be 3 pi on 4. Okay. Boy, so much for working ahead, hey? Now, so theta is in between 0 and 2 pi. Again, let's just prove we can create those answers. If I sub in 0, I'll get 0 plus or minus 3 pi and 4. Well, I'm only looking for the ones that are bigger than 0, so of those two answers, I'll write down 3 pi and 4. If I sub in 1, I get 2 pi plus or minus 3 pi and 4. But again, I only want the ones in between 0 and 2 pi. So 2 pi minus 3 pi and 4. And there's our answers we would expect. Well, some of us would expect anyway. Okay, so how we go with tan? Inverse tan of 1 on root 3? We're sure about it? We're sure? Pi? All right. So this is the one that is pi k. And yes, it is pi on 6 for that one. Let's just check and make sure it does work. If k is 0, I'll just get pi on 6. K is 1. Pi plus pi on 6. There's our two answers that are in between 0 and 2 pi. So I get a question like this. Sine of theta is equal to the sine of 5 pi on 7. Temptation is to simply say theta is 5 pi on 7. But that wouldn't be a general solution. So the general solution would be pi k plus minus 1 to the power of k inverse sine of the sine of 5 pi on 7. And then we could say the inverse sine of sine 5 pi on 7 is... Oh, we didn't trick him this time. 2 pi and 7, because inverse sine, remember, only gives answers out between minus pi on 2 and pi on 2. 5 pi on 7 would be the second quadrant answer for the sine function. So we're looking for the first quadrant answer. So 2 pi on 7, where k is an integer. All right, cos of 2x is cos of pi on 9. So this time it'll be 2x is 2 pi k plus or minus the inverse cos of the cos of pi on 9, which would be? Very good. See, look, walks in the door, bang, got it like that. Right? Yeah, because pi on 9 is an acute angle. Whenever it's an acute angle, the inverse cos, or whatever the inverse ratio is, it will cancel. So we've got 2 pi k plus or minus pi on 9, but that's what 2x is. We just want x, so we get pi k plus or minus pi on 18. And remember, it is important to specify k as an integer, because obviously if k is not an integer, it's some fraction, well, the solution's not going to work. It's got to be a whole number we're substituting in. All right. 1f.